Every useful program you write, from a simple command line tool to a complex server, needs to talk to the outside world. It needs to get information from you, the user, and it needs to tell you what it's doing. But how does it actually do that without crashing or slowing down when you type something unexpected? When I first started, I thought it was just magic. You type something, it appears. But there's a whole system underneath, carefully managing these interactions. Today, we're going to pull back the curtain and unlock the fundamental ways your C++ programs can talk to users, and just as importantly, how to leave clear, concise notes for future engineers, or, let's be honest, for yourself 6 months from now. By the end of this, you will master using standard cout and standard cin with their respective operators, left shift and right shift, for all your basic console interactions. This is the bread and butter of C++ programs. You will also learn to implement standard getline, which is crucial for reading entire lines of user input, especially when that input contains spaces. This is a common stumbling block for beginners, and we'll tackle it head-on. We'll differentiate between the humble new line character, \n, and the more complex standard endl, explaining their performance implications related to buffer flushing, knowing when to use which can save you real headaches down the line. Finally, you'll apply single-line and multi-line comments effectively to explain code intent and avoid common pitfalls. Think of input and output in C++ as a system of pipes, or streams. When your program wants to send data out to the console, it pushes that data into an output stream. When it wants to receive data from the keyboard, it pulls data from an input stream. It's a continuous flow, like water through a pipe. This stream abstraction is incredibly powerful because it means your program doesn't care if it's talking to a keyboard, a file, or even a network socket. It just pushes or pulls data from a stream. The operating system handles the messy details of where that data actually goes or comes from. It's a clean separation of concerns. In C++, these pipes are represented by objects found in the I/O stream header. You have standard cin for standard input, which is typically your keyboard. Then there's standard cout for standard output, usually your console screen. And for error messages, you have standard cerr, which is an unbuffered stream, meaning errors get displayed immediately. To push data into an output stream like standard cout, we use the stream insertion operator, which looks like two less than signs, left shift. To pull data out of an input stream like standard cin, we use the stream extraction operator, two greater than signs, right shift. These operators are overloaded to work with all the fundamental data types you'll encounter. Let's see this in action with a simple program that asks for your name and age. This is the basic structure you'll use for almost all console interaction. We'll include I/O stream for our input, output objects, and string for handling text. Here, we declare a standard string variable called name and an int variable called age. This line, standard cout left shift enter your name, prints the literal string enter your name to the console. The left shift operator inserts that string into the output stream. Then, standard cin right shift name waits for you to type something and press enter, extracting whatever you typed into the name variable. We do the same for age, a prompt with standard cout, and then standard cin right shift age to read the integer. Finally, we combine multiple pieces of data, literal strings, the name variable, another string, the age variable, and a new line character, all using the left shift operator chain together. This chaining is a common and efficient way to build output. When you compile and run this code, you'll see exactly this interaction. If you type Alice and then 30, the program will print, "Hello, Alice. You are 30 years old." It's a straightforward conversation between your program and the user, but there's a crucial detail about standard cin that often trips people up. Here's the common mistake. What if your name has a space in it, like John Doe? If you use standard cin right shift name, the extraction operator stops reading as soon as it encounters any white space. That means John gets stored in the name variable, and Doe is left in the input buffer, waiting for the next input operation. This can lead to unexpected behavior or skipped prompts. If you ran this code and typed John Doe for the name, then 25 for the age, the output would be, "Hello, John. You are 25 years old." The Doe part of the name is completely ignored by the standard cin right shift name operation. This is not what you want when asking for a full name. The fix for this is standard getline. Instead of using the right shift operator for strings, you call standard getline, passing it the input stream, standard cin, and the string variable where you want to store the entire line. This function reads characters until it encounters a new line character, including any spaces in between. Notice the crucial change. Standard getline, open parenthesis, standard cin, comma, name, close parenthesis. This will correctly capture John Doe as a single string. You still use standard cin right shift age for the integer because integers don't typically contain spaces, and the right shift operator is perfectly fine for single tokens. Now, if you run this corrected code and input John Doe for the name and 25 for the age, you get the expected output. Hello, John Doe. You are 25 years old. This is the robust way to handle multi-word string input in C++. Let's talk about new lines. You've seen me use \n for a new line character. You might also see standard endl. They both move the cursor to the next line, but there's a subtle, yet important, difference that can impact your program's performance. When I was starting out, I used standard endl everywhere, thinking it was more C++. Big mistake. The \n character is simply a character literal, just like a or 1. When you insert it into a stream, it gets added to an internal buffer. The operating system doesn't actually print anything to the console until that buffer is full, or until you explicitly tell it to. This buffering is an optimization to reduce the number of slow system calls. Standard endl, however, does two things. It inserts a new line character, and then it immediately flushes the output buffer. Flushing means forcing all the buffer data to be written to the console right then and there. While this ensures your output appears instantly, it also means your program makes a system call every single time you use standard endl. If you're printing a lot of lines in a loop, this can significantly slow down your program. Consider this loop. The first loop uses standard endl. Each iteration prints a number and then immediately flushes the buffer, causing a system call. The second loop uses \n. It prints a number and a new line, but the output is buffered. The actual printing to the console only happens when the buffer fills up or the program ends. For small programs, you won't notice a difference, but in performance-critical applications, or when logging thousands of lines, using standard endl repeatedly can introduce a measurable overhead. My rule of thumb is to use \n unless I specifically need to guarantee that output is visible immediately. For example, after prompting a user for input, or when writing to standard C for error messages. Now let's talk about comments. Think of comments as sticky notes you leave for yourself, or for the next engineer who has to read your code. They are completely ignored by the compiler. They exist solely for human readers. When I'm reviewing code, good comments are a sign of a thoughtful engineer. The most important rule for comments is this: explain why the code does something, not what it does. The code itself should be clear enough to show what it's doing. If your code needs a comment to explain what it's doing, then the code itself is probably poorly written and needs refactoring. C++ supports two styles of comments. The single-line comment starts with two forward slashes, double forward slash. Everything from the double forward slash to the end of that line is ignored. This is great for short, concise explanations. For longer explanations that span multiple lines, you use multi-line comments. These start with forward slash asterisk and end with asterisk forward slash. Everything between those two delimiters, across any number of lines, is ignored. One critical point: multi-line comments do not nest. If you try to put a forward slash asterisk inside another forward slash asterisk asterisk forward slash block, you'll get a compile error because the compiler will see the first asterisk forward slash and think the comment has ended prematurely. Here's an example of good commenting. This comment explains why we're using standard iOS-based scope resolution sync with std, io open parenthesis false close parenthesis, and standard C in .tie open parenthesis null pointer close parenthesis. These are performance optimizations for input-output streams, and their purpose isn't immediately obvious from the code itself. This is exactly the kind of context a future developer needs. Now, here's an example of a bad comment. Double forward slash declare an integer variable named x and initialize it to 10. This comment tells you what the line int x equals 10 does. You can already read that from the code. It adds no value, just visual clutter. Avoid comments that simply rephrase the code. You now understand three critical aspects of C++ programming. First, you can confidently use standard cin and standard cout with their respective operators to manage basic console input and output, and you know to use standard getline for reading entire lines of text. Second, you can differentiate between \n and standard endl, and you know the performance implications of buffer flushing, allowing you to write more efficient code. Finally, you can apply single-line and multi-line comments effectively, focusing on explaining the why behind your code, not just the what. Next time, we get our hands dirty with the actual building blocks of every program, variables, and fundamental data types.